Hi, in this video I'd like to explain a slightly different approach to so-called extended Euclidean algorithm. In my course I thought it's a very important theorem for a lot of things that's coming in this course, so I rather call this one a fundamental theorem of linear Diophantine equation, and in this video I will just abbreviate with this fundamental theorem, LDE. Well, the theorem states that if we have two positive integers a and b, and if d is this greatest common divisor, and we can obtain that greatest common divisor with this combination with a and b with some integers x and y. Since I'm assuming that you already know this Euclidean algorithm, I'm just mainly reviewing here, so I'm going over fairly quickly. So let's review the Euclidean algorithm. You start with this GCD symbol, then you replace this two item, kind of shifting this b to the first entry, and replace the second entry with a remainder. A is divided by b, and remainder replace it. So R1 is going to be always less than b, because that's a remainder and b was a divisor in this stance. So you repeat this process again. This R1 shifted, R2 is a remainder when b is divided by R1. Therefore R2 is smaller, and so on. You guarantee that eventually this kind of thing will occur. And you know that Rn is going to be the greatest common divisor. So I introduced it in following it from this information how we're going to pull out this type of information. The idea was that turning these two numbers into a column vector and see how we can use a matrix to go from this two pieces of number and these two numbers, a, b, and going to be R1. If you think about it, and this matrix formed like this will do the job. This b is shifted up, this 0, 1, and q1 is the quotient involved in this division algorithm. So if you write it like this, it's going to take you there. The process of getting from the second part in here to the third part is exactly the same process with a different quotient and different remainder. Therefore, if you pay attention to this part, and which is appearing in here, these are BR1. So if you multiply this matrix, we're going to get to R1, R2. So you keep multiplying these quotient matrix to the left. Then it's described here. We start with this AB. As we go through all this, you're writing this same shape of matrix to the left all the way to this part, and then you keep this shape, and we have column vector AB. And you know the second entry down here is the greatest common divisor. So you actually simplify this matrix and look at the bottom two part, and that'll give you x and y if you think about how this one is multiplied to this matrix. And that's kind of efficient way of doing this Euclidean algorithm and keep track of and quickly get this x and y information. Not only this is just an efficient algorithm, it tells you it's kind of proof that why this one happens. There is some x and y there, such that this combination will reach the greatest common divisor. Now this is the part of the different approach. I think it's a really cool proof, so that's why I'm introducing. It's a very different type of idea. So I don't think you can easily run into this type of idea. This is very, very refined idea over the long period of time mathematicians think about and develop this kind of nice idea. But whenever you feel like you got this kind of the beginning idea, and if you want to approach on your own, you should stop the video and try this thing yourself. And actually I encourage you to do that, because keep listening to mathematics, someone else speaking doesn't really make you learn this idea. So whenever you pick up this idea, you try to do this on your own. From there you really learn what's going on. And so I'm going to guide you through and encourage you in here and there, and stop the video and try to do this part yourself before we move on to the next part or something like that. So let's begin. So here's the already interesting setup. First set here is this all combination. We're going to look at all combination. The statement is about this combination. So we're going to look at all combination where we are varying x and y. But we're only collecting positive numbers. As we vary through all these integers, we have zeros sometimes and we have negative numbers. We're only collecting in this set A positive number. m here is just the multiple of this fixed integer m, and we have to describe what this m is. So m is the smallest element. It is kind of missing. I'm sorry about that. Smallest element of a. That's what this part's missing. So m is the smallest element of a. So I think we covered this principle in the beginning of this course, least integer principle, and we used axiom of choice and basic properties of integers to show to prove this one. So we're actually using it here. These are positive integers, therefore it has the smallest element. So we're using this least integer principle. So this is the setup. Next thing is not easy to kind of imagine, to pull out, but that's the difficult part. And what happens is that these two sets are equal to each other. So I wrote it here, and this is what we're about to prove. And think about how we are actually proving two sets are equal to each other. Sets are about the membership, whether it has a member in there or not. However they're organized, and that's not important part of the set. So when you're showing this, first you show all the members in A is in the B, all the members in the B is also in A as well. It turns out showing that B is contained in A is easier. So I wrote it down in here, and this is the part, this is a relatively easier than the other direction. So I want you to pause the video and see if you can prove that elements in a B is really element in A. So my proof starts like this. M, by definition, is the smallest element that is appearing in this set. So it looks like this. M is realized by this some sort of combination with x in 0 and y 0. And I'm going to pull out arbitrary element in here. That looks like this, mz. I used a different letter, if that's all right. Then I'm going to show it's in A. Of course, that you replace this m with this expression I have in here, and this is, we can rewrite this expression that looks like this. So here it is, mz, that's an arbitrary element in a B, looks like this, m times this particular expression in here. So we can rearrange it as a times some integer plus b times some integer. Anything that is in that combination is in an A, and this is, of course, is a positive because we pulled out as a positive number in here, because m is a positive, and we're multiplying the positive numbers. So I think this proves that any element in here is an element in an A, because it looks just like this one here. Right, let's prove the other direction. A is that combination set, and B is that multiple of Z. We're going to pull out arbitrary element from the positive combination part and show it's a multiple of M. And we approach that by proof by contradiction. In my opinion, this is a lot trickier than the other one. And let's think about how the beginning part goes. It's proof by contradiction. So here, I pulled out, I label it like this x1 and y1. This is not arbitrary element. I'm assuming there is at least one element in that set A such that that is not in a B. And that would violate that statement. Everything in that element in A must be an element B. So I'm supposing here there's one element with this combination that is not in the B. That would be the negation of our conclusion. For those who want to try on their own, the idea is using division algorithm here, just one time. One time using the division algorithm will take care of the rest of the part. So if you'd like to try on your own, so think about that, how to use the division algorithm, and from here to pull out some contradiction. Try it. So here's how the standard algorithm goes. So this element is not in B. I'm going to show you what the B is. Here's a B. B was a multiple of M. Everything here is divisible by M. And here we are assuming that element here is not in B. That means it's not divisible by M. So if you divide that element by M, by division algorithm, M is there, divisor, and Z is here as a quotient, or it's going to be a remainder because we assume it is not divisible, not in a B. The remainder is going to be positive number, and this is always less than M. So that's the statement. you get out of division algorithm. So if you feel like you can do the rest of the part from here, you should try now. Try this part, rest of the part on your own. So here's how the rest of the part goes. It's about that r. R is not supposed to be there, so I isolated r, moving everything over there. And m was actually the smallest element. That's another thing. M was the smallest element in that set A. A is here. M was the smallest element of A, so it looks like AX something, so I call X0 and Y0. That's why it looks like this. M is replaced by that. I adjust it a little bit. So the whole thing is now, you can see, can be written as a combination of A and B. So A here, everything's factored out, and B is there, and these two terms, everything factored out. It looks like this, and the right-hand side is R. So where is the contradiction? The contradiction is that R, its fairly small number, is even smaller than M, and it is a positive, and it is written as a combination. So this is a combination of A and B, therefore is a member of that set A, but it turns out that's an element that is even smaller than M, but the definition of M was the smallest element that you find in that combination set here. So R was a type of, this is supposed to be A, sorry about that. So I fixed it. So R is supposed to be in A because it's a combination, but it turns out that element is smaller than the smallest element. That's a contradiction. There is a smallest element, nothing else is smaller than that M. So this is a contradiction, therefore there's no such element. Now we have established this interesting statement that all this combination, as long as they're positive, forms this perfect set of a multiple of one element, which is M here, the smallest element that appears in this set and right here. This type of refinement of this set theoretic description, a more multiplicative structure, is not something you can just pull out by looking at this problem for the first time. It's a very refined algebraic modern approach to these type of problems. So next thing is, of course, that okay, we have this nice description, but what has it got to do with the greatest common divisor? It's about this greatest common divisor and this combination in here. So greatest common divisor we're going to denote by D and also AB here. M is the smallest element, also this forms perfect positive multiples of M. This is about the minimality of minimum element and things like that, and this greatest common divisor about the divisibility, what divides A and B and things like this. So I guess definitely the connection is this divisibility, right? So here's a spot I want you to challenge yourself and stop the video and see if you can make a connection between D and an M. So this is the first connection I came up with. In my opinion, this is easier to pull out. It's more natural. It's just out there. M was the naturally described as you make a connection. The smallest element in there, of course, it has this description. Divisibility we know about whatever is involved here is something that divides A and B. This D divides both A and B in there. So D appears as a factor in here. Of course, D appears as a factor in there. Therefore, D divides M. D is here. D divides M. So that makes D smaller than M. So kind of one connection we have in here. And this is even better connection. But we end up at using just this one to show actually M is equal to D. But this is, of course, the better information. The second one is, I think it's harder to pull out. But let me give you this summary of what just happened in here that might give you an idea to what to look for. Is the following. If you look at this argument, lots of this type of thing happens when you prove something abstractly like this. D is supposed to be the greatest common divisor of this, but I don't think I really use the property that D is the greatest common divisor of A and B. This argument still works when I pull out some smaller divisor for A and B, and that still divides M, and we have this statement. So this is not really sensitive to our choice of D, that is being a greatest common divisor of all. So in the second part, when you utilize this part, maybe you can pull out the other direction, these, m is less than d or something like that. So this is something I'd like to I want you to try. So pause the video and see if you can pull out the greatest common divisor part, and we want to eventually show m is less than d, right? And compare that with the greatest property. Alright, here's the thing what was difficult. It was very special element you have to look at in here. A and b are both positive integers, so a is in that element, a times 1 plus b times 0. And b is in there, a times 0, b times 1. Both are in there. And because of this multiple description, mx description, a is a multiple of m, and b is a multiple of m. So it looks like this. mx is a and my is b. And this description says m is a common divisor of a and b. So here m is a common divisor and d is the greatest common divisor, and there is this inequality. So which together with these two, we show m is equal to d. Here it is, that's the conclusion. So if you look at it here, if you look at all positive combination of a and b, and think about the smallest element, and we show that this forms a multiple of m's, and that m is indeed the greatest common divisor of a and b. I like that. So if you think about its entire argument, it's very, very different. It's not algorithmic. It is very using just existence and this, putting some structure to that elements in there, and using this property, we just touch the existence of everything that was claimed in this fundamental theorem of linear differential equation. So it's different approach. It definitely uses division algorithm. This type of phenomenon goes all the way to the unique factorization domain, and it lines up the chain of reasoning. At the bottom, there is this division algorithm. Division algorithm makes everything work for us. And it's a very different type of proof, but it still uses division algorithm. That's the important part to note. And I thought this is a cool type of proof that if you enjoy mathematics, and often many of us enjoy this type of mathematics as well, but algorithm is cool too. Thanks.